Alright, here's an example using the relationship between, using material properties to have a relationship between stress and strain. So we have this rigid plate and it's supported by bar 1. Bar 1 is a 2-force member. And by a double shear pin connection at B. Bar 1 has a length of L1, so we're going to write that both in the given and on the figure. So given is L1 equals 60 inches. So this is 60 inches. And the area of bar 1 is A1 equals 0.47 inches squared. And the elastic modulus of bar 1 is E1 equals 10,000 KSI. Then we have some information about the pin at B. It has a diameter. So we have the diameter, the pin at B equals 0.438 inches. And then there's going to be this load P applied. Then the strain in bar 1 is going to be 960 microstrain. So strain in bar 1 equals 960 microstrain. And it's going to elongate. And that makes sense if we're looking at this picture. P is going to pull it this way, putting this in tension. Okay. So, and then the dimensions are currently not shown. So let me tell you what those dimensions are. We have 20 inches and 12 inches. Okay. So we're supposed to determine the magnitude of load P. Okay. So what is this load? And the average shear stress in pin B. So find for part A load P, and for part B shear stress pin B. Okay, so this comes down to finding forces. So we have to find P. There's going to be 2 reactions here, and there's going to be 1 reaction here. So if we draw a free body diagram just to orient ourselves a bit on what we know and what we don't know. Since this is a rigid plate, that's going to be what we draw our free body diagram of. The forces and reactions on the plate. We have P up here. We have the force in bar 1 here. Then we have a reaction in the y direction at B and a reaction in the x direction at B. So currently we have 4 unknowns and 3 equations. But what can we solve? So if we know the strain in bar 1 and we know the elastic modulus of bar 1, then we could use Hooke's law to calculate the stress in bar 1. So we can calculate F1 using Hooke's law which is E equals stress over strain, because we know both E, elastic modulus, and strain, and normal stress, which would be sigma equals F1 over A1. So we'll solve for sigma, and then we can solve for F1. Okay, so first we're going to turn the strain that is currently in microstrain to just strain. So strain 1 equals 960 microstrains. So we're going to multiply that times 1 times 10 to the negative 6 strain equals 1 microstrain. So the strain is 0.00096. Okay, now I'm going to use Hooke's law. So E equals stress over strain, meaning that stress equals E times strain. E is 10,000 kips per square inch, and the strain is 0.00096 strain, meaning that sigma equals 9.6 KSI. Okay, so now we can use that normal stress. It's the normal stress in bar 1. And they gave us the area of bar 1, so that's this. And then we can calculate the force in bar 1 so that we know this force, and then we'll only have 3 unknowns and 3 equations. Okay, so then we have that sigma equals F over A. So we have F1 equals 9.6 kips per inches squared times the area, which is 0.47 inches squared. 0.47 inches squared. So that equals, I get F1 equals 4.512 kips. Alright, so if we have F1, 512 kips, and then we know that this is 20 inches, and we know that this is 12 inches. I can solve for force P and the reactions at B. So, going to copy that, and I'm going to start a new page. So, I'm going to use the free body diagram to solve for P and the reactions at B. Here's my free body diagram. So I'm going to sum the moments around B. It's going to equal 0. That'll equal F1, we'll make a positive moment around B, times, and then P will make a negative moment around B. That will be 12 inches. So this really equals 4.512 kips times 20 inches minus P times 12 inches. So I get a P equal to 7.52 kips. And that's my first answer. Okay, then I need to solve for Bx and By, so I'll do sum of the forces in the x equals 0. So that equals P plus Bx. Now I know that P, 7.52 kips, plus Bx, all that equals 0. So Bx just equals a negative 7.52 kips. So all that means is that I drew Bx the wrong way, which is fine. It actually goes that way, which makes sense because P goes that way. So we know that. And then we sum the forces in the y direction. Those equal 0, and that equals By minus F1, which equals By minus F1 is 4.512 kips. So then we get By equals 4.512 kips. And now we can do part B. What was part B? Part B was the shear stress in pin B, so we have to determine if it was in single or double shear. The pin at B, rigid plate is supported by double shear. Double shear pin connection at B. Okay, so that means we'll divide our area by 2, and the diameter of the bolt is 0.438. Okay, so we need to calculate shear stress, which is tau equals shear force over the shear area of pin B. Okay, and it's in double shear. Okay, so the first thing we need to do is we have Bx and a By, and those are the components of the force at B, but ultimately they sum up to some resultant force, and that's what the shear force will be, is the resultant force. So we need the resultant force at B. So that would be B equals square root 7.5152 squared plus 4.512 squared. So the resultant force at B is 8.77 kips. Okay, now we need the shear area. So we'll calculate the area of pin B. So this is cross-sectional area. So that's going to be area of B equals pi over 4 times the diameter of 0.438 inches squared. And that equals 0.15067 inches squared. Alright, but then double shear so shear area, which is AV equals 2 times the area of pin B. So this is 2 times 0.15067, and we get 0.3013 inches squared. And then the shear stress of pin B is tau equals V over AV, which is 8.77 kips divided by 0.3013 inches squared. And the shear stress equals 29.1 inches squared. All right. So we found all of our useful information from the problem and what we needed to know. We drew our free body diagram to get oriented on what we did know and what we needed to know. We figured out that we could calculate F1 using Hooke's law and the normal stress equation. Once we had F1, we could use our free body diagram, and then we could solve for P and the reactions at B. And then with the reactions at B, we could find the resultant force, double shear, and solve for the shear stress.